this video, we're going to look at the definition of Brønsted-Lowry acids and then some examples. So we're going to start with a little review of Chemistry 20 and modified Arrhenius theory. So modified Arrhenius theory told us that an acid is any substance that produces hydronium when reacted with water. So an example of an acid would be something like hydrochloric acid. And when this substance reacts with water, it produces hydronium, H3O+, and chloride, Cl-. Hydronium is a water molecule basically with an extra hydrogen. So it has 3 hydrogens, lone pair, and an overall charge of +1. So it is what forms, and that is our definition. And the modified Arrhenius definition of a base was a substance that produces hydroxide when reacted with water. So an example of a base would be something like ammonia, NH3. When reacted with water, we're looking for that hydroxide to form OH- plus NH4+. So for the modified Arrhenius definition, we're really looking at the product in that reaction with water. So we're looking for either hydronium or hydroxide. And this definition doesn't really give us a lot of information when we don't react with water, but react with other substances. And so this is why we're going to look at the Brønsted-Lowry definition instead. So the Brønsted-Lowry definition of an acid is a substance that is what we call proton, so an H+ donor. So it's called a proton because when hydrogen loses an electron, it's just a bare proton. And a base is what we call a proton acceptor. So instead of looking at what these species form in water, we're looking at the species themselves. So if we look at the same reactions as last time, so if I look at HCl, and I still react it with water, so same reaction we saw on the last page, H3O+ and chloride minus. So what's happened here is that HCl has lost a proton, and it's that proton has been transferred to water, which has gained a proton. With ammonia, NH3 aqueous plus water, we form hydroxide, same as before, and ammonium, NH4+. Now in this scenario, ammonia has gained a proton, and that proton has come from the water. So it's proton acceptor. And the reason that this is important is if we were to react an acid with a base, so if we react our HCl acid with the ammonia base that we've been talking about, we're not going to produce either hydronium or hydroxide, but instead, the hydrogen from the acid will transfer to the ammonia and will form a chloride ion and will form ammonium. Now, in this example, we have 2 what we call conjugate pairs. So hydrogen and chloride, hydrogen, chloride, and chloride, this is a conjugate acid-base pair. They differ by 1 proton. Okay, and this ammonia and ammonium is also a conjugate acid-base pair that also differs by 1 proton. Okay. So within acids and bases, we can have something called a polyprotic acid or base. All this means is that it's going to be able to react multiple times as an acid or a base. So if it's an acid, it will donate multiple protons. If it's a base, it will accept more than one proton. So an example of a polyprotic acid would be something like H3PO4, where we have 3 hydrogens that are donatable. An example of a polyprotic base would be something like PO4 3-, and that 3- charge tells us that we can accept 3 protons. So H3PO4, the first proton will give us H2PO4-, then HPO4 2-, and the final reaction will give us phosphate PO4 3-. When phosphate reacts, it'll first form HPO4 2-, then H2PO4-, and finally phosphoric acid. We can also have something called an amphiprotic species. So the prefix amphi means both. So an amphiprotic species is a species that can act as either an acid or a base. So it can donate a proton, or it can accept a proton. There's one exception to this rule, but what you're going to be looking for in your acid-base table is you're going to look for a substance with a hydrogen and a negative charge. So that hydrogen, this is our donatable hydrogen, and that negative charge, that is our proton acceptor. So you're looking for those two features. The one exception to this in your acid-base table is water. Water is amphiprotic. And the reason is we have this structure with 2 lone pairs of electrons. So within water, this hydrogen is a donatable hydrogen. So it can lose that hydrogen to form OH-. This lone pair, this is a proton acceptor. So it can form a bond with a hydrogen ion, and there we would form H3O+.